Okay, alrighty, here we go with the next section in our note pack. This section is all about how the shape of a graph. We've learned before that a graph can tell us something about its derivatives, and now we're going to look specifically what derivatives tell us about the graph of the original function. Okay, so 5.8, this concept, we're going to be able to use first derivatives to find the increasing and decreasing behavior of a function. So let's first draw a graph and talk a little bit about what that might mean. So here's a function. It has both increasing behavior, where the values of y are increasing on an interval, and decreasing behavior, where the values of y are decreasing on some interval. And if we look at the increasing places, we know that along here, all those tangent lines are positive slope tangent lines. Therefore, the derivatives would be positive. And if we look where the graph of the function is decreasing, we can see that the slopes of all the tangent lines there have a negative slope or a negative derivative. So the derivatives can tell us something about the increasing or decreasing behavior. If we know that the derivative of the function is greater than 0 on some interval. So on an interval, okay, and we're going to call that interval I, then we know that f of x is increasing. The y values are getting bigger, okay, on that interval. And then conversely, we know that if the derivative is less than 0 on I, that same interval or some interval, then f of x is decreasing on I. Okay, it's decreasing on that interval. Okay, so let's look at a function. F of x equals x cubed minus 6x squared plus 9x plus 2. And we are asked to find the intervals where f of x is increasing and decreasing. So this time we are looking for an interval. So what we would probably need to do is we would probably need to find out where the derivatives are 0. Okay, because where the derivatives are 0 is where the increasing behavior changes to decreasing behavior, or where the decreasing behavior changes to increasing behavior. So if we find those zeros, we can find the places where possibly the increasing or decreasing changes, and then we can look at what's actually happening to that derivative on either side of the 0. So if I were to find this derivative, it would be 3x squared minus 12x plus 9, and I'm going to go ahead and factor out a 3, so that would be x squared minus 4x plus 3, and then that factors into x minus 3, x minus 1. Okay, and so therefore we know that the derivative of x equals 0 at x equals 3 and 1. Okay, so that tells us where the low points and the high points of this might be, and therefore where that might be changing its derivatives. All right, so what we're going to do next is we are going to make a first derivative sign charts. We've made sign charts before in this class for velocity and acceleration. Now we're going to do it for the derivative. And the process is the same. We list the factors, and we're going to list all the factors, just because sometimes one of those factors, if it's a number, might be a negative number. So we want to get in the habit of listing those factors. And then down here on our number line, okay, we're going to put all the places where the derivative is 0. This number line, unlike the velocity acceleration number line, does not start at 0. It can continue in both directions as long as the function is defined everywhere, and in this case it is. So let's put on our key points here. The derivative is 0 at 1, and the derivative is 0 at 3. So now let's pick a point to the left of 1 and see what's happening with the derivative, because right here we know the derivative is 0. But let's look to this side of 1. At this side of 1, 3 is positive. At this side of 1, this factor is going to be negative. So if I put 0 in there, I get negative 3. And if I put 0 in here, I get negative 1. So if I multiply all those together, positive times a negative is a positive. So in this case, f prime is increasing at that point because f prime is positive, okay, and therefore the function is increasing. All right, let's look between 1 and 3, and let's pick 2. Well, 3 is always positive. 2 minus 3 is a negative number. 2 minus 1 is a positive number. If I multiply those all out, the derivative is negative. Therefore, f is decreasing on that interval. And now let's look to the right of 3. Well, 3 is always positive. If I pick 4, 4 minus 3 is a positive number. 4 minus 1 is another positive number. So the derivative, positive times a positive times a positive, is a positive. Therefore, the function is increasing on that interval. Okay, and so now I need to answer the questions. Find that interval where they're increasing and decreasing. So f of x is decreasing on the interval from 1 to 3. Now notice I use open brackets because it is not, in fact, decreasing at 1 or at 3. It is 0 there. And then f of x is increasing on the interval negative infinity to 1 and 3 to infinity. Okay. All right, what are the critical numbers of f of x above? The critical numbers are x equals 1 and 3, because we know critical numbers are where the derivative is equal to 0, okay, or where the derivative is d and e, and we found that the derivative is 0 as at 1 and 3. So note that at 1, the derivative, sorry, I didn't write at 1, at x equals 1, the derivative changes from positive to negative. Okay, and at x equals 3, the derivative changes from negative to positive. That's going to become pretty important as we move through this unit, noticing what is happening at those critical numbers. How are things changing on either side of them, and what does that tell us about the function? Okay, so use the first derivative test to find the local extrema of a function. Okay, so suppose c is a critical number of a continuous function. If the derivative changes from positive to negative at x equals c. Okay, so the derivative changes from positive to negative. That means the slope changes from positive to negative at c. Okay, so let's just draw a little graph of what that might look like. Okay, here's c, and at c, the derivative is 0, and the slope is positive before c, and then negative after c. Okay, then what can we say about f of c? Well, then we can say that f of c is a local max of f of x. Okay, we don't know necessarily that it's an absolute max, but we know that is a local max. All right, well, if we know that the derivative changes from negative to positive at x equals c. All right, let's draw a little graph of that. So here's a little graph, and the derivative changes, here's c again, the derivative is negative, and then all of a sudden at c, it starts going positive. Well, look at that, then we can say that f of c is a local minimum of the original function. All right, so we've looked at f of x changing from negative to positive and from positive to negative. There is a third possibility. What if the derivative of f of x does not change sign? Oops, does not change sign. At x equals c. Okay, then f does not have a local max or local min at x equals c. And what might that look like? Well, that's our cubic function, okay? Looks like that. We know that the derivative right here is 0, and however, the slope of those tangent lines remain positive throughout. Okay. Page 2. So for f of x equals x to the third, that function that we just looked at, okay, back here. So let's talk about that information that we just put in our notes on the other page. So since the derivative of x changes from positive to negative at x equals 1, there is a local max at the point 1, comma, well, let's put 1 in here. 1 cubed is 1, minus 6 is negative 5. Negative 5 plus 9 is 4, plus 2 is 6. So that is our local maximum, okay? And since the derivative changes from negative to positive at x equals 3, there is a local min at the point 3, comma 2. If I put 3 in the function, I would get 2. So now we have a way of determining where our local maximums and local minimums are. Up to this point, we knew where to find absolute maximums and minimums. Now we know how to find local ones. All right, definition, a new definition in calculus, and this is the definition of concavity, okay? And we're going to draw some pictures here to hit this point home. So a definition of concavity. If the graph, you know what, before I do that, I'm going to actually show you concavity here. Okay, so I have some function and it does this. Okay, does something like this. Don't want to make it that sharp up. It does something like this. Okay, this is an example of a piece of a function. It might not be the whole function, but this function is concave up. Okay, and I remember that by that U right there, okay, kind of like the umbrella is pointing in the U shape. The umbrella is not pointing in the correct shape. It's kind of like an upside down U, okay, and we use the abbreviation for that as concave up. I'm going to draw another picture over here to show you, in contrast, what concave down is. Okay, so this is what concave down is. It would be concave down on that interval. And we use the abbreviation CD there. All right, so let's see if we can get a more official definition of what concave up and concave down means. Okay, so if the graph of f lies above all the tangent lines on some interval I, okay, then it is concave up. On I. Okay, so let's see what that means. If the curve or the graph of f of x lies above all the tangent lines on that function, then that function is concave up. 1 minute. Okay, I wanted to run and get another color here. Okay, so I got my other color, so let's draw in some tangent lines. Here's a tangent line right there. You can see that the curve is above that tangent line. Here's another tangent line right here. You can see that the curve is above that tangent line. Here's another tangent line, okay? You can see that the penciled in line is above all those red lines there, okay? And so because the curve lies above all the tangent lines, it is called concave up. So what is happening with those tangent lines? Well, those tangent lines are getting steeper and steeper and steeper, right? Here, maybe that slope of that tangent line is 1/2. Here, maybe the slope of that tangent line is 1. Here, maybe the slope of that tangent line is 2. So f prime is increasing, and that's going to become important in a minute. Okay, let's draw another picture of a curve that is concave up. Okay, so here's another curve that is concave up. How do I know that? Well, let's see. I have a tangent line right here, okay, and that tangent line is below the curve, or the curve is above it. Here's another tangent line right here, okay, the curve is above it. And if I draw this one, here is another tangent line. So there's those 3 tangent lines. And again, it is concave up. Now, is this still true? Is the derivative increasing there? Yes, it is, and let me explain to you why that is so. The derivative is increasing because over here, okay, where it's maybe a little bit steeper, f prime might be -2. But down here, where it's not so steep, f prime might be negative 1/2. Okay, and so as I'm increasing in the x direction, my derivative is also increasing. The value of the derivative is increasing. -1/2 is definitely bigger than -2. Okay, that's going to become an important concept. Please put a little asterisk next to this section if you're not really quite sure what I'm saying there. It will probably need some further explanation there. Okay. Okay, let's go back and look at concave down. So the definition then of concave down is if f lies below all the tangent lines, on I, okay, then it is concave down. Okay, so here we go. Let's draw the tangent lines. Here's a tangent line right here. Here's a tangent line right here. Here's a tangent line right there. Okay, and we can see from all of those that those tangent lines lie below. Now, what is happening to all those tangent lines as I'm getting bigger and bigger in the x direction? Well, here, this tangent line probably has a slope of 2. Here, that tangent line might have a slope of 1. Here, this tangent line might have a slope of 1/2. So in this case, f prime of x is decreasing. Okay. All right, and let's look at another example. Let's draw this curve right here. Okay, this is concave down, I'm going to say. Okay, or CD. And let's look at those tangent lines. Okay, here's a tangent line. Here's a tangent line. And here's a tangent line. Okay, and all of those tangent lines lie above the curve, so the curve is below it, therefore it is concave down. And again, the derivative is decreasing. Up here, that slope might be -1/2. Here it might be -1. Here it might be -2. -1/2 is bigger than -2, and so therefore the derivative is decreasing. All right, so please make a note of that if we need to talk about that concept again tomorrow. All right, so we're going to use the second derivative to determine the concavity of a function and find the points of inflection of a curve. So here, second derivative. We've never used the second derivative for anything before, and now we're going to start using it. And the second derivative is what tells us about concavity, okay? So the second derivative leads to decisions about concavity. So if the second derivative of x is greater than 0 for all x in some interval, then the graph of f is concave up on I. If the second derivative of x is less than 0 for all x in I, then the graph of f is concave down on I. All right, so maybe let's look over here and talk about are the second derivatives positive or negative? Now remember, second derivative is the slope of the first derivative. All right, so here I have the first derivatives, and the slope of these first derivatives is going to be positive, okay? All the slopes of these will be positive slopes, okay? This is going to take some more explanation in class. So in both of these cases, the second derivative is going to be 0, okay? And I'm going to explain this more in class, in class on Thursday. And here, this one, the second derivatives of x, we know, are going to be less than 0. All right, so we'll talk about that more in class. A point on a curve, f of x, is a point of inflection if x is continuous there and the curve changes from concave up to concave down. In other words, the second derivative changes from positive to negative, or from concave down to concave up. Well, that means it changes from negative to positive. Okay, and so if that's happening there, if the concavity is changing, if the signs of the second derivative change, we have something called a point of inflection. And we will actually abbreviate that in this class as a POI. All right, so let's try to make sense of all of this from that original problem that we were working with on the other page, and see if we can at least get close to some understanding here. And then, of course, I will clarify, and we'll look at this together in class on Thursday. All right, so find the intervals of concavity and the points of inflection for this graph. Well, we already found that the first derivative of this function was 3x squared plus minus 12x plus 9. And since we're talking about concavity, we know we need the second derivative of f. So we're going to find the second derivative right now. That's going to be 6x minus 12. Okay, so concavity happens where the second derivative changes from positive to negative or negative to positive. So we need to first figure out, where is that second derivative equal to 0? So we set that second derivative equal to 0, and we get that it's equal to 0 at 2. So what we want to look at is that second derivative on a number line, okay, at 2. 2 is the only possible place where something is happening with the second derivative. Okay, so let's look at this side over here. Let's put 0. If I put 0 in here, I get that the second derivative is negative. So this is going to be concave down here. And on this side, if I put 3, I get a positive number. So the second derivative is positive. So it is concave up. So my intervals of concavity, it is concave up from 2 to infinity, and concave down, and you can use the abbreviations if you want, from negative infinity to 2. Okay? And so therefore, the point 2, and what do I get if I put 2 in there? Let's figure out what that point is. If I put 2 into the original function, I get 8. 2 squared is 4 minus 24 plus 18 plus 2. So that's going to be negative 16. So 2, 4 is my point of inflection. 2, 4 is my point of inflection. Okay, so let's sketch a graph using all this information that we have found. Okay, so up here we found some local maximum and minimums. We know where the derivative is 0 from the page before. Okay, we know where those critical numbers are. The critical numbers are at 1 and 3. We know where it's increasing. We know where it's decreasing. So we can put all this information into a graph here. So let's kind of sketch this graph. Okay. Pretty much all our values are positive values. So this function right here, we know crosses the x-axis at 2. We know that because the function is, or y-axis at 2, this function right here. So if I put x equals 0 in there, I get that y equals 2. I know at 1, okay, at 1, I have a local maximum at the point 1, 6. And I know that 1, 2, 3, 4, 5, 6, okay, I know that it is increasing from negative infinity to 1. Okay, it is increasing from negative infinity to 1. And then it turns the corner there, okay? Turns the corner, and it has a minimum at the point 3, 2. So here a local minimum at the point 3, 2, okay? And it is concave down, and then it switches to concave up, and then it takes off in that direction. Okay, so here is a sketch of the graph, and that point of inflection, 1, 2, 3, 4, happens right about here, where all of a sudden the slope of those lines are going to be more underneath it. Okay. Okay, so there is our graph. Sorry, you guys couldn't see any of that, could you? Well, that rubs. Okay, so here's the local maximum, here's the local minimum, here's the point of inflection, local min at the point 3, 2, local max up there, and in fact, that's not an absolute max because we don't have a closed interval. This function goes on and on forever, but this is a local max, and there is our graph. Okay, we are going to stop there, and we are going to finish up the rest of this tomorrow in Thursday in class. We're going to talk about the second derivative test to determine local maximum and minimums, and then we're going to put it all together once again by doing this example problem. Okay, so come to class with your questions, and I will see you then.